So yeah, thanks for the organizers for setting up this wonderful school and for inviting me, giving me the opportunity to speak here. And as Vika said, I'll talk a bit about zero knowledge and multi-party quantum computation in the quantum world. And this is, okay, I try to cite all the relevant papers, but the idea is that I did some collection of things that are in the literature, some things that are very recent and hot topics in the field. And let's see how it goes. But the idea is that I'll give an overview of almost everything that was, or a slice of what was done in zero knowledge and multi-party computation in the past years. But in order to start, we should think about, okay, when you look to cryptographic primitives, we have a plethora of them. And one question that cryptographers would ask is, okay, how can you propose new protocols, and how can you prove security of these protocols? So do you have to do it one by one? So every time that I propose a new primitive, I have to propose a specific protocol for it and prove its security, or can you have a smarter way? And luckily, we have the latter. So, and the idea is that you have reductions. So for example, you shouldn't expect that you go in nature and you find a beautiful chairs and table like this. What you expected to do is you can go there, find some wood, and find a hammer, and then construct the tables, the table and the chairs yourself. And of course, you can go one step further. You don't expect to have a hammer in the nature, so you can find wood and stones and build the hammer yourself. So the idea is that trying to find the smallest components that you can propose and prove security by themselves, and then construct more complicated things from it. And we have been very successful trying to do this type of reductions. So for example, we know that a lot of primitives can be built only from 1A functions, so functions that are easy to compute but harder to invert. But on the other hand, we have some no-go theorem that says, for instance, that we cannot build some cryptographic primitives from 1A functions only. So we need something stronger than that to have I don't know, oblivious transfer or multi-party computation. And in order to try to classify which are the primitives that can be built from simple and self-contained assumptions, cryptographers and complexity theorists, they have defined a few worlds where we could live. So for example, we can define the world minicrypt as the world where 1A functions exist. So we know, for example, that several primitives such as PRF or I don't know, secret key encryption, they can be built. Oops. They can be built only from 1A functions. But as I said, we don't believe that everything can be built from 1A functions. So we can define the second world that we call cryptomania, where now we assume that public key encryption exists. And then we can have plenty of other awesome cryptographic primitives built from public key encryption. But that's not all. So recently, we have seen that we have this third world where we have indistinguishable obfuscation, where we can we're morally crypto complete. So the idea is that if you're able to do I/O, then almost everything that can be done with crypto can be done there. But there, of course, okay, here I'm assuming that crypto is possible, because there are also the worlds where, for example, we can solve NP in practice. And this is very good for some reasons. So for example, we can solve optimization problems, so we can solve TSP and so on. So that's very good, with the downside that you don't have crypto in this case. So we cannot do secure transaction in the internet, so you have some mixed feelings. And of course, the worst case is that we don't have crypto and we don't have and we cannot solve NP. So that's the worst of all possible worlds where we can do nothing. So that's the big catastrophe. But everything that I said so far only concerns the classical world. So so far we just assume that we have classical communication, all the parties are classical. And by the title of this winter school, of course, our question is how do quantum resources affect these reductions or these 5 worlds that I defined. And putting quantum resources on the table, on the one hand, it's good because now we allow these honest parties to share quantum resources. And as we saw in the talk by Roten, for example, these allow us to do things even that are impossible to do with only classical resources. So for example, the parties can exchange keys in information with information theoretically security, which is trivially impossible classically. But on the other hand, as we saw with Shor's algorithm, the problem is that quantum resources also helps malicious parties. So if you have a purely classical protocol, and now the adversaries are able to buy or construct a quantum computer, now they could be able to break these cryptographic protocols. And the goal of in quantum cryptography is trying to see which of the sides wins. So can you use quantum to beat quantum, or can you find smarter ways of doing things classically in order to prevent quantum adversaries to win? And we have seen several such results in previous lectures in this school. But there's also another way where quantum could play an important role, is that, okay, we have a quantum computer. Now parties, they want to do quantum computation. So for example, they're doing quantum chemistry, they're doing a Hamiltonian simulation or whatever they want to do with quantum computer. But now, then we can start thinking, okay, what happens if they want to do a joint computation on that, such that all the parties don't want to reveal their quantum state? So how can you achieve protocols for having now quantum cryptographic functionalities? And my idea in this lecture is try to discuss these 2 questions. So how quantum resources affect classical reductions, and some protocols for quantum functionalities, but just specific for zero knowledge and multi-party computation. Why these 2 topics? So first, zero knowledge proofs, they are a central tool in cryptography toolbox. So there are plenty of applications or plenty of protocols that use zero knowledge proofs as a building block. So studying them in the quantum setting is fundamental in order to prove quantum security. And multi-party computation, in some sense, is the most general functionality that you could build if you don't care about the number of rounds or of interaction between the parties. Because when we talk about multi-party computation, we're just we're just asking, how can parties compute a general function jointly and privately? And a more specific agenda. So in zero knowledge proofs, I'll try to explain a bit how we have zero knowledge for NP in the classical case. Then study these zero knowledge proofs against quantum adversaries. And finally, going a step further, trying to propose new zero knowledge protocols, but now for quantum proof. So so this third one is having a quantum protocol for a quantum functionality, as I mentioned before. On the MPC side, I'll discuss a bit how classically we have multi-party computation from a primitive called oblivious transfer. Then I'll show this very recent protocol where we show that OT is in, sorry, it's not a recent protocol, this recent proof that shows that OT can be built with quantum resources and one-way function only. And we know that that's, okay, at least that's expected not to be possible in the classical world. And finally, I'll discuss a bit on protocols for having multi-party quantum computation. So quantum parties that want to do a joint computation on their quantum data. Is there any question about, okay, what are the goals of these lectures?
For now, there are no questions in this Slack.
Okay, thanks. And okay, so let's start. So our goal now is to have to show, okay, to discuss zero knowledge in the quantum world. And okay, one property of quantum zero knowledge is it lies in this intersection of these three different fields. So it lies, so we need a bit of cryptography, a bit of quantum computing, and a bit of theoretical computer science. So explaining these concepts or explaining quantum zero knowledge for such a broad audience is always a challenge. And I'll try to assume the minimal possible knowledge of each of them. But of course, if something is not clear or if something is too slow, let me know, and I can adjust the pace with that. But without further ado, let's start with it. And to start, instead of talking about zero knowledge, I'll give a step back and talk about how to extend the notion of proofs. How computer scientists in the 80s they redefined our concept of proofs that we had since ancient Greece. And as a context, we can like earlier, like in, I don't know, 60s. Complexity theorists they managed to define what we mean for efficient proof verification from a computational perspective. And to do that, they define this complexity class that we call NP. And we say that a problem, like a problem, is in NP if you have this polynomial time verifier, so an algorithm that runs in polynomial time, but receives some message or some proof from this untrusted prover, and this untrusted prover can run in an arbitrary unbounded time. But the only requirement that we want is that this message that that this prover sends to the verifier has polynomial size. And then this verifier, given some input to this language and this proof sent by the prover, should decide to accept or reject. And the requirements that you have for NP is that for every positive instance, there exists a message sent by the prover such that the verifier accepts. And you can think about this of X being a mathematical statement, and this is just requiring that for every true statement, there exists a proof that that checks the truth of such statement. Our second requirement is that for all negative instances, so for every instance that is not in this language, no matter which message this prover sends, this verifier should reject. And again, here we should just think that if X is a false mathematical statement, no matter which proof you have, it should not prove the correctness of such a false statement. And NP has a central place in complexity theory. And because of the central, because of its importance, people start thinking, okay, how can you generalize it? And the first way of generalizing it is, for instance, considering messages that are sent back from the prover and the verifier. So here we have an interactive proof system, and the idea is that now the verifier is able to ask questions or to challenge this prover that will answer back these challenges or these questions. And what we want from these interactive proof systems, again, is that for all true statements, there is some strategy that could run in exponential time. We don't really care about this, but there exists some strategy for the provers that makes this verifier accept after interacting with this prover in many rounds. And for false statements, no matter what this prover does, like no matter what are the strategy of these provers, this verifier should reject with high probability. And it was later shown that actually everything that can be solved with these interactive real systems can be also solved with polynomial space. So showing that given interaction to the verifier should increase a lot the computational power of this proof system, so we can prove many more problems. And again, these interactive systems, they have been fundamental in the development of several topics in computer science complexity theory. But here we are in the cryptographic, like in a winter school of cryptography, and we want to see a bit of the consequences of interactive proof systems for cryptography. And for that, I'll need to ask. So I'll add more restrictions or more constraints on which type of interactive proof systems we want. And the main topic of this part of the talk is talking about zero knowledge. And a zero knowledge proof is just an interactive proof system where we add the extra requirement that the verifier learns nothing when you have a true statement. So whenever the statement is true, the verifier should not learn anything else that on top of knowing that the statement is true. It seems weird how to define these, and I'll do it in a second. But one important point is that we not only want that this honest verifier that interacts with proof learns nothing, but an arbitrary malicious verifier that might deviate from the original protocol should learn nothing as well. Okay, and now, okay, yeah, and now my goal is to try to define more concretely what do we mean by a verifier not learning nothing from the interaction. Okay, I think there's no question, so let me move on. So as I said, a zero knowledge protocol is just an interactive proof system with a possibly malicious verifier. And we assume that this verifier, after interacting with this prover, has some output. And this output could be has a probabilistic nature. So this verifier could run, like, I don't know, toss some coins and decide to output based on these coins. And here we just define as X as the distribution of the outputs of this verifier. And in order to show that this protocol is zero knowledge, we have to come up with a polynomial time algorithm that's a simulator that can have access, a black box access to this malicious verifier. And the simulator also has some output that whose distribution is denoted here by Y. And it's important to notice that this polynomial time simulator does not have any access to this prover. It acts on its own. So with just a polynomial time algorithm that could run the verifier internally, but not to the prover. And the notion of, okay, zero knowledge is asking that you have to come up with a simulator such that for every verifier, these two distributions are indistinguishable. And more concretely, when you're talking about computational zero knowledge or zero knowledge, like in this talk, I'll focus on computational zero knowledge. So whenever I say zero knowledge, it's computational zero knowledge. I just mean that there exists no efficient distinguisher for the distributions, meaning that for every polynomial time algorithm A should behave morally the same if she's given an input, a sample from the first distribution or a sample from the second distribution. So the output of A could be different only up to a negligible factor. Is there any question about the definition of zero knowledge?
No.
Okay.
There's no questions, but let me ask one. So does the prover here choose the instance himself or herself?
No, okay. No, we can think that the instance is given to all the parties from a, I don't know, from a trusted third party. For now, let's think about they have them like from to start with.
Okay, thanks.
Sorry, there's a question on slide. So does it mean the algorithm A needs to be deterministic?
No, not necessarily. A could be randomized. Yeah, it's just being polynomial, probabilistic polynomial time.
Thanks.
And okay, this is morally what we want from zero knowledge, but we need to strengthen a little bit. Is that, for example, we would like zero knowledge protocols to be composable, and in particular, we want to be able to sequentially repeat zero knowledge protocols. And in order to do that, we have to add an extra piece in this scenario, where we think that both the malicious verifier and the simulator, they could receive some side information. And here denoted by this classical information Z that's sent to both the verifier and or to simulator. And we want it to be zero knowledge if for every such Z, the output distribution is still indistinguishable. Okay, and the idea to see why this is this somehow is required for composable is that if you think that you run this protocol again on parallel or sequentially, you can just think that the output of this first verifier will be given to the second verifier, and we want this second verifier to still not to learn anything from the interaction of the prover.
There's one more question on the Slack, and that is, what is the reason that we go from perfect probability to high probability with interactive proofs?
Okay, the main reason is that if you have perfect probabilities, then you go back to NP. So you cannot prove, at least for okay, as I mentioned before, okay. On one side, for true instances, it's fine to have perfect probability, but for no instances, like accepting false statements, like okay, saying that we want to reject false statements relative to 1, makes us back to NP. So we need to have it in order to this class to be meaningful or more useful.
Thanks.
And just for completeness, we can define other notions of zero knowledge. For example, we could denote the statistical zero knowledge, where the case where we can come up with a simulator such that the distribution X is statistically close to the distribution Y. Or even further, we could define perfect zero knowledge where these two distributions are exactly the same. But again, for this talk, I'll just focus on computational zero knowledge, because this is most important for cryptography. And if you have never seen zero knowledge, it is the bread and butter of cryptography, so it's used everywhere. And it has, yeah, as I said, it has several applications. And let me just give an example of how this zero knowledge could be used. So we could imagine that you have two parties, Alice and Bob. And Alice, she has some input X, and she wants to just compute some function that's publicly known and on X and give it to Y. But she doesn't want Bob to learn anything else like she doesn't want, in particular, she doesn't want Bob to learn X. So of course, Bob could compute all pre-images of Y, but we wouldn't like him to learn specifically which pre-image you're talking about. And the idea is that but on the other hand, Alice wants to convince Bob that Y has some pre-image, at least, okay? So in order to convince Bob of that, she can just prove in zero knowledge that there exists some X such that Y is equal f of X. And in this case, by the zero knowledge property, so by the simulation, Bob is not learning what specific what specific X Alice has. And by the soundness property, Bob can be sure that this Y is coming, has this property, that it has some X such that Y is equal f of X. And this is a very simple application, but some sort of this is used everywhere. And in order to have a zero knowledge proof that allows us to compute this, we need to have a zero knowledge protocol for problems in NP. So notice that here we have an NP statement, right? We have you have this Y is an input, and you can prove that there exists an X such that Y is equal f of X. So it will be having a zero knowledge protocol for problems in NP will allow us to prove such statements. And in this talk, I will specifically talk about zero knowledge of the three coloring. And three coloring is an NP complete problem. So proving for this specific problem, we prove for all problems in NP. So let's move on to this protocol. Let me explain how this protocol works. So the idea here is that this verifier, she has some description of some graph, and she wants to decide if there is a way of color each of these vertices in a way that all the vertices that are connected by an edge, they have different colors. Or on the other hand, she wants to show, or if this is not possible, for every coloring, there exists an edge that connects two vertices with the same color. As I said, this problem is NP complete, so we expect it to be hard in the worst case. And but it's in NP, right? For example, the prover can just give the coloring to the verifier, and the verifier can check this. So let's first try to understand this NP verification and understand why it's not zero knowledge. So as I said, this prover can run in unbounded time. So this prover can find such a coloring and send, for example, this prover can just send this coloring to this verifier. This protocol is complete, like meaning that if the graph is indeed three coloring, the verifier will get convinced because she can check if all of the edges they connect two vertices with different colors. And it is also sound because if the prover send a coloring that's not valid, the verifier will check if this this edge and see that these two colors are the same. But assuming P different of NP, this protocol is far from being zero knowledge, because if it were zero knowledge, this simulator could be just used as an algorithm to compute the coloring of a graph. So, okay, yeah, under very standard assumptions, this protocol is very far from being zero knowledge. But we'll tweak it in a way that, okay, then it will become zero knowledge. But to tweak it, we need some crypto, and the crypto that we need is bit commitment. And if you've never seen bit commitment, this is what we can see as a cryptographic safe. So we can imagine that you have these two parties, the committer and the receiver. And the committer has a message that he wants to commit to the receiver, but not necessarily open. So in other words, this committer wants to put this message in a safe and send the safe to this receiver, but keep the key the password to open the safe private to this committer. So as long as this receiver does not have the key, this receiver should not be able to read this information that is inside it. Later on, this committer could decide to send this password or this key to this receiver, and then with this key, this receiver could just open the safe and see the message and read the message. Okay, so when you're talking about protocols for bit commitment, we have these two phases where in the first phase, the committer and the receiver, they generate this commitment to this message, and on the second phase, the committer opens the commitment to the message in a way that when we are in the first phase, the receiver should not learn anything from this commitment of M. For this receiver, M is completely hidden from the first message. But on the other hand, we want this we want this to be a commitment. So we want that C can not be able. We don't want C to be able to open in the second phase for a message M prime that's different of M. Okay, so I want to define, like, I'll come back to bit commitment later when we're talking about multi-party computation. But for now, I want just to keep intuitively what means, like the security definitions of that you want for bit commitment. Is there any question? So I'll move on. So let's go back to this and define this zero knowledge proof for three coloring. And this is by GMW91. And here, as we said, the prover can run in a amount of time, so the prover can compute the coloring of this graph. And in our zero-knowledge protocol, the very first thing that the prover will do is permute the colors of this coloring. So he can define a bijection between the scholars, and a random bijection between the scholars, and change the colors of these vertices. Then the prover put each color of each vertex in a different safe, and send all the safes to this verifier, but keeping the keys that open each of the safes. Then the verifier decides to open the safes of a specific edge. So she decides, for example, that she wants to open this edge, and she tells the prover, give me the keys that open the edge AC. And the prover should just answer back with the keys that open these two safes. And with these keys, the verifier can open the safes and check if the colors are different. It's not too hard to see that this protocol is complete, because if there exists a coloring that is a valid through coloring, then the prover can just behave honestly, and the verifier will always accept, because whenever the verifier opens these two safes, the two colors will be different. And this is also sound, because if the prover sends a commitment of a coloring that's not valid, by the binding properties of the commitment scheme, we have that when the verifier chooses that specific edge that has the two colors, she will open to two values whose two values are exactly the same, and should reject. And this should happen with probability 1 over the number of edges with inverse polynomial, and fine enough. So if you want negligible soundness, you could just repeat it sequentially. But more important for us now is how can you, so it's about talking about zero knowledge. So I'll prove now that this protocol is also computational zero knowledge. And intuitively, why this is the case? Notice that the verifier here, whenever she opens these two commitments, she only sees two random different colors, right? Remember that the prover re-randomized the colors, so the only thing that she sees are two colors that are different. So this is the intuition. But when you're proving zero knowledge, we need to be a bit more formal, and you need to show this simulator that is indistinguishable from the view, or from the output of a potentially malicious verifier. So let's define this simulator. So sorry, is there any question about this, about the protocol?
There was a question why the colors are randomized, but I think that might have just been answered, or if not, then it's going to be answered now, right?
Okay, if this question is keeps on, yeah, I think I already gave an intuition, but if not, I'll go back to that.
Okay.
So let's define a simulator for it. So as I said before, we want this simulator to be given this side information Z, and the simulator behave as follows. First, it will give this. So the simulator can run this malicious verifier. So the simulator just gives Z, forwards it to this malicious verifier, and the simulator just pick. So the idea is that the simulator, you have the simulator, and the simulator will behave as the prover against this malicious verifier. So the simulator will pick some random edge E and send commitments that send a random a commitment of a coloring that's correct on edge E. So we have this graph. So we have a graph. Let's say you have this graph, and the simulator will pick some edge, some specific edge, and the simulator will just choose a coloring that would work for this edge. For example, red here, and green here. Oops, no, I didn't. And green here. So we have two different colors for that edge. And for all of the all other vertices, for example, she could just color it with an arbitrary color and send all of these send commitments for all of these colors to this v tilde. Then in the protocol, this v tilde should answer back with some value e prime. So in the honest case, e prime is just a random edge. But since v tilde might not follow the protocol, we just have the assumption that v tilde sends some edge to the simulator. And whenever the simulator receives this edge e prime, we have two cases. First, we have that e prime is equal to e. And if you have the case where e prime is equal to e, then the simulator could just open the coloring of this edge. And the idea here is that this verifier v tilde could not see the difference, because everything else that does not have a valid coloring is hidden by the hiding property of the commitment. So every invalid color here, or every part of this invalid coloring is inside the box, inside the safe, so v tilde cannot distinguish the difference. So in this case, the simulator could just open the commitment and output whatever v tilde would output in this case. Of course, the hard part here, what happens if E is not equal to e prime? So what happens if the challenge sent by the verifier is not the one that the simulator guessed in the first place? And for example, this would be problematic if the edge that the simulator, sorry, that v tilde chose is this one, for example. Oops, is this one, because then you have two colors that are the same. But here we're in a classical world, so the verifier v tilde is a classical algorithm. So we could just rewind to the step 2. So we could just record all possible operations of v tilde and go back to the place where before we send the commitment and start over. Okay, so we could just remove. So we could just rewind. So the term that we use it is rewind. So it means that we we just rewind. So we just forget the message that we sent here and start over. And the idea is that whenever you do this, you have a fresh start. So you pick a different edge uniform at random. And sorry. Whenever you have a fresh start, you pick a different edge uniform at random. So every time you should you should guess the correct one with probability 1 over m. So just to recatch this sketch of proof, we have that if E is equal to E prime, the output of the simulation is computationally indistinguishable of the interaction of v tilde that interacts with the prover. because of the hiding property of the commitment scheme. So everything that does not have the proper coloring will be hidden in the safe. And okay, an important point to notice is that since V tilde is computationally bounded, the distribution of challenges sent by E tilde cannot depend on the committed values, because if it could depend, then we would have problems. And in order to prove this, we can just show that if the distribution of the challenges change according to these committed values, then this V tilde can be used to break the commitment scheme. And from this second part, we have that the probability that you guess the correct edge that to be challenged by the verifier V tilde is at least 1 over m minus negligible. And this negligible just comes from the probability, the probability that the V tilde can break the commitment scheme. Is there any question on the sketch of proof of why the simulator should be indistinguishable of the verification? Okay, if not, I'll...
One question,
and
that is how this rewinding is different from forcing V tilde to give a certain challenge E prime that the simulator can choose in advance.
First, we can never force. For example, V tilde could always ask an arbitrary, let's say you have a graph, V tilde could challenge a specific and deterministic edge, so you cannot never change the way that V tilde will ask. What I said is that every time that you rewind, you pick a different edge. So when in this corner case where V tilde answers a deterministic challenges a deterministic edge, you hit this deterministic edge with probability 1 over m. So it's not how to force the challenge, it's how can you pick a different edge, and what's the probability of falling in a challenge asked by this V tilde.
Thanks.
Okay, so now we have a classical zero knowledge protocol for NP, and this is secure against a classical adversary. And the question is, what happens if V tilde is now a quantum algorithm? So what works or what breaks down in this case? But in order to answer this more formally, let's give one step back and talk about classical zero knowledge against quantum adversaries. So as you had so far, you have when you want to prove zero knowledge, you have this classical prover that interacts with this classical but potentially malicious verifier. And the only thing that you want to change in this protocol is that now this verifier could be quantum. So the verifier has run a quantum algorithm and decides to send some quantum message to this prover, but this prover somehow does not see the quantumness and answer back, and so on. And whenever we have such a malicious quantum verifier, we could assume that after interact with this prover, this verifier V tilde just outputs some arbitrary quantum state rho. And in order to prove zero knowledge, again, we want to come up with a simulator. But now, since the verifier is a quantum algorithm, so we should also give this computational power to the simulator. So we have a quantum algorithm that runs in polynomial time and might have black box access to, or in order to do the simulation, yeah, could interact with this quantum malicious verifier in order to output some a new quantum state sigma. And as we had in the classical case, not only want to do this like in the standalone notion, like in the standalone version, but we could also assume that both the verifier and the simulator, they could receive some quantum side information. Okay, so each of them receives some polynomial size quantum state psi, let's say. And in order to show that this protocol is zero knowledge against quantum adversaries, our goal is to show that rho is in the quantum state rho is indistinguishable from the quantum state sigma. So more concretely, this asks that for every side information psi, and for every quantum polynomial time algorithm A, the behavior of A when given this quantum state rho should be the same as the behavior of A when given when given this input state sigma up to a negligible factor. Any question? Okay. And as in the classical case, for completeness, we can just extend this notion to statistical zero knowledge, meaning that the trace distance that Henry explained of these two states should be negligible, or also just perfect zero knowledge, meaning that these two states are exactly the same. So they are rho and sigma, they are the same reduces, the same dense matrix. Okay, so our goal now is to try to understand this GMW protocol, if it's also secure whenever we consider these quantum verification algorithms. Okay, so let me move on. And in order to prove this, I'll start with a simpler task. So instead of considering an arbitrary side information, let's consider we want to have a classical one. So the state psi is just a classical value z. And let's try to understand what happens with the original simulator that we had in this case. Okay, so again, the simulator just gives z to this quantum verifier, pick some edge, commit to a coloring that is correct on the edge, receive a challenge. If so, the idea is that if what to try to see what if E is different of E prime, we would like to rewind to step 2, or just open the commitment if they're the same and forward the output. So let's study what's happening with the simulator for quantum malicious verifiers. And in order to do that, let's understand what's the state of V tilde right before V tilde sends this challenge to the simulator or to the prover in the real case. And for simplicity, I'm assuming it's a pure state psi, pure state phi. And without laws of generality, so we can just write down the state phi as a superposition of E prime in some state gamma E prime. So, and each of these elements in superposition, they have some amplitude alpha E prime. And so again, this is just without laws of generality because I'm just picking some orthogonal basis for this first register, that's the message register, and another possibly not orthogonal states gamma E prime that the verifier kept on her private register. Okay, is there any question of why we can define the verifier's registers like this, or?
No, I don't think we have any questions so far. So
okay, good. And okay, so the idea is that the verifier V tilde would send this message register to the simulator. And the simulator will check if E is equal to E prime or not. So so the idea of the simulator, you would measure this register, the first register, the message register, and it will get some value E prime, some classical value E prime with the corresponding probability. And whenever the simulator gets this value E prime, the state that the verifier and the message had, it collapses to this pair E prime, gamma E prime. Okay, and this is just how measurements happen in quantum mechanics. Then we have again the two cases. The first case is when E prime is equal to E, and the point, okay, if you do the calculations, you see that all is good, all is still good. So the state of the verifier is morally the same as it would be in the in the real protocol. But the problem with the step 5, like rewinding to step 2, is that since we did the measurement, whenever you do the rewinding, is like by quantum mechanics, you need to run the inverse of this operation of the verifier. But now the input, like the state on which you apply this rewinding, is this post-measured state. So it's not the state phi that where you have the superposition before. So it's not this state, but it will be the undoing, this inverse operation on the post-measured state. And in general, these two states will be the same. So whenever, so the bottom line is that after, if you have that E is different of E prime, whenever you try to do a rewinding, then you're not back to the same place. Like you're now back to a very different place here. Okay, I think all is good. Okay. But we can, like, in the specific case of where we have this quantum state psi to be a classical value, we can tweak it. We can tweak this protocol. So in particular, instead of rewinding to step 2, we could say, okay, let me just start over. Let's say that I can reset V tilde, so I can go back, can throw away a copy that you have from V tilde and get a new one. And I can go back to step 1 and give Z to this new version of V tilde and run everything again. And if you do this, like this resetting, everything that I said before, like in the purely classical case, should work. Okay, and the idea here is that since you reset V tilde and start from the beginning, whenever you pick a different edge here, like whenever there is you're in step 2, the state that this V tilde will have there will always be the state phi, and in this case you guess the correct one through L1 over m again. But okay, oops. But the main problem here is that this does not work if you have a general size of quantum side information. And in order to see this, is that if you have some, okay, if you give, okay, instead of giving Z, you give psi, like this quantum state psi to V tilde. You can try it once. If you have E equals E prime, you're all good. But when you try to reset V tilde and go back to step 1, imagine that you can reset V tilde, that's fine, but now you don't have access to psi anymore. Because of no cloning theorem, you're just given one copy of this state psi, and that's it. You have one try to run the simulator, And if at some point you screw up, then there's no way back. Okay, so we need to come up with new techniques that will allow us to do some sort of rewind whenever you have an arbitrary quantum state as side information.
There's a question on Slack, and I allow myself to rephrase it a little. Basically, the question is about the runtime of the simulator, because it somehow depends on meeting this condition E equals E prime.
Yes, but the point is since you pick E uniformly at random and modulo negligible factors, you always have this probability to be inverse, like 1/m. So the runtime of the simulator is always order of m, right? Because you can just do some tail inequality, some tail inequality, and you have that some tail bounds, and you have that this is the runtime of simulator modulo all the operations. The problem with the malicious setting, or sorry, the full quantum setting, is not about the runtime at all. It's just about having a single copy of psi. Yeah, I don't know if I answered the question that the person asked, or...
Let's assume you did. Otherwise, we will take it later in the end of the lecture.
Yeah, this person can just ask it again, if or clarify. But okay, so the point is, okay, now, as I said, we have to come up with smarter solutions if we don't have this very strong assumption. But actually, you can ask why do we care about an arbitrary quantum state psi as a side information? And the point is, if you don't have this, we cannot, for example, we cannot sequentially repeat this protocol. Because if you have this malicious verifier, and you want to do it twice, so we have v tilde and v tilde prime, you have to think that whatever this malicious verifier does should forward it to the second verifier, and now we have an arbitrary quantum state here. So we have some, let's say, some psi prime. So we really need to deal with this general case. Just for example, to make soundness to be negligible small.
I think that there's one more question, and that is kind of to elaborate a little bit more on the intuition why this quantum side information prevents rewinding.
Okay. Let me just do this so I have some space. So let's assume also, okay, let's assume that this side information is some pure state psi, just for simplicity, so it's easier to write it down. So everything that I wrote here is correct, right? So you still have that phi is this pure state that can be written in this way. And again, the simulator still does some measurement and gets some E prime, like whenever the simulator gets this message, she just measure E prime, and in this case, the state collapses. Once you have this collapse, if you have that E prime is equal E, again, all fine, but the problematic part is whenever E prime is different of E. And there are two cases. First, you try to rewind, but we already saw that like this naive rewinding that's just applying the inverse operation, this inverse operation of the verifier on the post-measurement state, this won't suffice, because this is in particular different of applying this inverse operation on the original state phi. So naive rewinding does not work. but we had, instead of having this naive rewinding, we had the fact that okay, what happens if you reset v tilde and go back to the first place? But notice that whenever you give, okay, so what I'm saying here is that you have the state phi, you measured it, so you have let's say e tilde, e prime, gamma prime. What I'm just saying, reset it, is throw this away and try to run v tilde again. But to do that, I need to give this quantum state psi to v tilde, but I don't have it anymore because I used psi to compute phi and I threw it away. Okay, so in this case, in this case, I cannot just reset v tilde. As I said, this solution of resetting won't work anymore because you cannot feed psi again to v tilde. And okay, yeah, I think I'm finishing. So with that, I'd like to finish this this first part of the lecture, and the continuation I'll explain how to deal with the general case. But I'm happy to answer more questions on this.